Hi everyone, here we are going to see about the Unit 5 continuation. So let me see the topics today. What are the processes are you going to use in the digital signal method? So the second order FAR filter. So here we have used the second order FAR filter. So that is a FAR filter means finite impulse response filter. So here there is the x of n is given as an input, then it is passed into the delay processor. So when one delay is given, it will be given the h of 0. Next the x of n minus 1 input will be passed into the delay. So here we have given the h of 1 as a input. Next we have to pass the x of n minus 2. For that h of 2 is given. All these inputs are multiplied together and passed into the adder. So this adder will be gives the combined together the output of the input of the x of n values and then passed into the single output value as a y of n. So that is y of n is equal to h of 0 into x of n plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2. So this will be the second order FIR filter formation. So next thing will be that organization of the single samples and the filter coefficients for a second order FIR filter implementation. So here is that we have to pass this x of n plus 1 to x of n minus 1, x of n minus 2. So here AR of 1 is given, that is the delays are given for each and every input values. For x of n we have used the h of 0, x of n minus 1, h of 1, x of n minus 2, h of 2. So all these things are together form a single output and then it should be passed into the MAC. So MAC as a processor. So the MAC processor will be passed this output value as a y of n and that should be organized as a single sample and filter the coefficients into the FAR filter implementation process. And nth order FIR filter implementation. So here is the in one of the side there is a coefficient memory and the another side that is the data memory. So the coefficient memory should be represented as a of 0, a of 1, a of 2, etc. up to a of n minus 1. And the data memory should be represented as x of n, x of n minus 1, x of n minus 2, etc. up to x of n minus n plus 1 and y of n. So all these together forms the output data memory. So from a of 0 and x of n both are combined together and sent into the MAC accumulator. So after that it should be passed into the P. P value will be guessed as one of the input and the accumulator output will be given as another input. So both the values are added together and send the output to the accumulator. Accumulator will store the data in the output value, that is the y of n. So this is the nth order FIR filter implementation. Next, FIR filter pseudo code. So the load loop count will be the data adder that should be initialize the coefficient and registration. Loop that is a p new 0 accumulator and p registers that is equal to ai of into x of n minus I. So that is accumulator new is equal to accumulator old plus p old. So decrement coefficient registers and data adder. So that should be shown that x of n minus I, that is x of n minus I minus 1 for next iterations. So decrement loop count is known as the DNZ loop. So that is the accumulator sent to the y of n as a values. So FIR filter pseudo code should be stored as a filtering process and it should be maintained in the processing the data. So this will be stored as an output method of the single way. Next, the typical the Dsp architecture. So the typical Dsp architecture is shown here. That is the program memory is given here, and the instructions and the secondary data are given here. So first, the data address for generator is given, and the data address for generator DM PM. So both are given here. So PM means that is the program memory, and DM means data memory. For both we have the address generator. After the generator, it will be passed into the program sequencer. So this program sequencer will store the programming methods, and then pass into the all the data values that have been stored in the program sequencer. After that, it pass into the instruction cache. So the instruction cache will moves the instructions to the registers, multipliers, ALU and shifter. So first it should be stored in the register, then that register value will be multiplied together. After that, if it is an addition means that is a arithmetic logical unit, it should be stored in the arithmetic logical unit. After that, if the value is higher means it should be shifted values into the other bases. So DMA buses should be given the input or output controller and pass the output value as a method. Next, Salient features. So repeat MAC instructions that should be performed auto increment of both coefficient and data pointers. So freeze up the program memory bus for fetching the coefficients. That should be circular buffer. So it should manage the data movement at the end of the every output computations, and it should be handle the precisions. That is accumulator guard bits, saturation mode, shifters. So both the left and right shift should be occurred in the digital signal processing method. Types of multipliers used. So there are three types of multipliers are used. One is the array multipliers. Next thing will be the multipliers based on modified Booth's algorithms. So these are the used for multiplying processes, and it should be maintain the methods of modifying the array data. Next, product computation unit of the simple multiplier for 4-bit unsigned numbers, that is x and y. So here we have given the x and y values. So this x and y values should be stored as a P0, B1, B2, B3. Okay, likewise we have mentioned. So that should be passed into the AND gate, and then added one by one values and stored in the output as a method of merit. So multiplying the x and y, the summation unit of the simple multiplier is shown here. So first the a, b and c, both three values have been passed into the adder. So adder will be added the values and then pass the sum value and the carry out values. So likewise, first we are passing the P0, that is x0, y0, x0, y1, x0, y2, x0, y3. So if we are passing 0 value as one of the input, and x1, y0, x1, y1, x1, y2. So all these together passed to the next, and then given to the x2, y0, x2, y1, x2, y2, x1, y3. Okay, next thing passed into the x3, y0, x3, y1, x3, y2 and x2, y3. After that it will be passes the 0, then all the values are being combined together, and then we have get the x3, y3. So the output will be given as P1, P6, sorry, P0, P1, P2, P3, P4, P5 and P6 and P7. So these are the multiplying process of the simple multiplier method. Combinational array for Booth's algorithm. So that is the basic cell B. So here the H and D values are given, that is 0, x, 1, 0, 1, 1. So that is 0, x means its function will be the z is equal to a, no operation should be done. And c x z, that is a plus b plus c add is given. Next c add z, c sub z, that is the a minus b minus c, that is the subtraction should be occurs in the functional process. So there is a b value has been given, c value also given. So it all the things should be passed into the I bit adder or subtractor. After that we will get the c out, and h and d values also given. So b and z as an output of the processing method. So the Booth's algorithm will be boot together and forms the one of the output values as a single value, that is the carry out output. array multiplier for a 4 cross 4 bit numbers using the basic cell B. So that is we have used the 0 value. So that is the 0, y3, 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 y2, 1, y1, y0. So next is x naught. When we are passing the x naught, the b values are added, basic cell is added. Next x1 is added to the basic cell, and x2 is added to basic cell, and x3 is added to the basic cell. All these values together and forms the p0, p1, p2, p3, p4, p5 and p6 values. So these are the array multipliers of 4 cross 4 bit numbers and using the basic cells.